Hi there. Continuing with our talk about thermochemistry, we're going to learn today how to calculate standard enthalpies using the standard heats of formation. So remember that we said that enthalpy here was the heat lost or gained in a reaction. So we can calculate that based on how much energy it takes to create something. So if we look down at our list here, or let me remind you about one thing. So here's a really important thing to remember. Remember that the H of reactant is equal to products minus reactants. That's why in exothermic it's negative, because the products have less energy than the reactants. So if we look at our chart here, these are our standard enthalpies of formation. So the important thing to remember here, that these are for products. Right? They're for products. So if something's listed in a reactant, you have to change the sign. And I'll go over that as we go. So these are the standard enthalpies of formation for products, and they're kilojoules per mole. So if we have more than 1 mole, we have to multiply it. So for instance, if we have H2O gas, right? So if we see H2O gas here, so let me explain what we're talking about. So if I have O2 plus H2, right? So if I have O2 plus 2H2, I get, let me move that. All right, let me move that over here. So I have O2 plus 2H2 yields H2O gas, right? And these are gases. Right. So since oxygen and hydrogen are elements, their standards of formation are 0 because they're elements. But our standard of formation for water is negative 241.8 kilojoules per mole. Oh my goodness, my writing is awful. So let me do that again. So that was 241.8 kilojoules per mole. All right. Now, when we do this, I get 2H2O. So I would have to multiply this by 2. Right? So it produces 2 times that in a standard reaction. So that's how much energy was released. Remember, it's negative, so it's exothermic. So this is released. Okay? So that's what we're talking about when we're talking about using standard enthalpies. So let me show you some easy equations, right? So we have this first one. So the way your strategy for doing this is we look at our substances here and make sure you take note of the phases. So we'll just find them up here and write them down. So I have sodium hydroxide, solid. I have a solid here. So this is negative 426.7. HCl gas, I have it up here, is negative 92.3. I got sodium chloride solid, which is down here, which is negative 411.0. And I've got water gas, which up here again was negative 241.8. All right, those are all in kilojoules per mole. So remember, this is going to be products minus reactants. So an easy way to do this, you can rewrite the whole thing, right? Or you can do this. Right? So it's products minus reactants. So the thing I was going to tell you earlier is, since these are all for products, you can simply just make those positive and add it all together. And you get the right answer, right? All of these have a coefficient of 1. So you could simply add those together. So I get 420.7 plus 92.3 minus 411 minus 241.8. And I get 134. I got 3 digits. Well, I get to the 10th, right? Because it's an addition. So I get 133.8. Oops. So my delta H is negative 133.8, and so that is an exothermic reaction. Okay, so fairly easy. So if we take, let's take the second one. So I've got CO2. I'll write that down below. So I've got CO2. And CO2 gas was negative I got O2 gas. Remember, O2 is an element. So that's going to be 0. Let me make that a little better again. It's going to be 0. Yields 2. And I made a mistake here because this wasn't CO2, that was CO. So carbon monoxide is, oh, I had it right, negative 110.5. CO2, let's find that, is negative 393.5. Okay, so if we go about our business again, right? Remember, this is in the reactants, I have to change the sign. But remember, I have a coefficient of 2. So I have to multiply that by 2. I have a coefficient of 2. So I have to multiply that by 2. So let's see what we get. So I have 2 times 110.5 plus 2 times a negative 393.5, and I get negative 566. And it's still exothermic. If you got a positive number, that would be endothermic. Okay, so I think you know how to do those now. So you can try the rest if you want. Right, so that is using a one-line equation like this. So we can figure out enthalpies using a one-line equation. I could take these and I could plug it into the values I find up here. Right, but what Hess said, so remember we talked about reactions. So if I have a standard exothermic reaction, I have reactants and products. So I have my reactants here, my products here, and here, remember, I have activated complexes. And those activated complexes are intermediate reactions that take place on my transition as I'm trying to go from my reactants to my products. Okay, so what Hess's law said is if I took all of the enthalpies of the activated complexes or the intermediate reactions, it wouldn't make a difference because the enthalpy is still just the difference between the reactants or product at the end. So let me show you how you calculate that. All right, let me erase all this stuff. Okay, so here we go. So we have our reaction here. So 4 moles of ammonia and 5 moles of oxygen yield 4 moles of nitrogen monoxide and 6 moles of water gas. So here are my three, here's my 3 intermediate reactions. So the method here is we have to compare these reactions with the one at the top. Okay, so you'll see that I have a nitrogen here. There's no nitrogen up here. I have oxygen. Oxygen here is a reactant, and it's a reactant here. And I have nitrogen monoxide here. And I've got nitrogen monoxide there as a product. Okay, so remember when I said you leave oxygen for last? We're going to leave oxygen for last. But we're going to start looking at things. So if you see here, I have 4 moles of that and 2 moles of that. Right? So I'm going to have to multiply this whole equation by 2 to get 4. Right? So because I multiply that by 2, I'm going to have to eventually multiply that by 2. All right? So if you look at my equation under it, right? So I've got N2 here, I've got H2 there. I don't have either one of those up here. And I have ammonia here. Now ammonia here is a product and it's supposed to be a reactant. So what I'm going to have to do is I'm going to have to change the direction of this. If I change the direction of that, I have to change the sign here because I changed the direction. But again, I have 2 and I'm supposed to have 4. So I'm going to have to multiply this whole thing by 2 as well. So I have to multiply this by 2 as well. All right. So if we come down here now, I have 2 hydrogens here. I have 6 there. I have 3 an oxygen here. I've got 2 oxygen. So both of those together would make 5. And I have 2 waters here, and I'm supposed to have 6. Okay, so I'm going to have to, so my water's in my right spot, but I'm going to have to multiply this by 3. Right? So now I have 2 oxygens and 3 oxygens, so I'm going to end up with 5, which I'm supposed to end up with, and that's kind of where I want to be. So if you remember, we changed some things. So let's see what we did. And because I multiplied that by 3, I'm going to have to multiply that by 3. Before I go to solve this, let me make sure if I did it right. Let's cancel out things we don't want. 3 oxygens, right? I've got 2 oxygens, so I got 5. So that checks out. I got 2 nitrogens here. I don't want to have any nitrogens. So these nitrogens here are reactants. But since I put my arrow here, these ones are products. So I can cancel those out. My hydrogens, I have 6 hydrogens. Remember, they're products because the arrow is pointing here. I have 6 hydrogen products. I've got 6 hydrogens here in the reactants. So I can cancel out my hydrogens. Right? I have 3 times 2. I have 6 waters. I'm supposed to have 6 waters. So that's right. I have 4 nitrogens. 2 times 2, which is 4. So that checks out. And I have 2 times 2, so I have 4 ammonias. And I'm supposed to have 4. And that checks out. So everything checks out. All right, so now I can just go ahead and solve. All right? So just go ahead and add those up. So I have a negative 180.5 times 2. And I have 2 times 91.8. I have 3 times a negative 483.6. So I get 162. All right, so let me correct this answer because I wrote it down wrong. So that was negative 16,282.0 kilojoules. So that's the enthalpy of the total reaction. So if we did the enthalpy using our standards up here, I would essentially get the same number. So you can do the one below if you want, but that's how you do it. And if you have any questions, I'll post a board so you can ask them and I'll solve some more stuff for you. All right.